you very much. It's very, very nice to be here. I'm always very happy when I'm in Israel. I don't know if it's a few years, but it's at least a few months or maybe a year or two that I've been interested in the kind of topics I would like to discuss today. And I will start right away with not too much introduction, and I prepared a talk which is somewhat quantitative with some mathematics, and so if there is any question, anything that is unclear, please interrupt as much as you want. I'm sure you will anyway. So when I started coming from physics and from neuroscience, when I started hanging out with people who do who work on cognitive questions, I was wondering why they walk around and say Bayesian as if it's some kind of magic incantation. Because for me it was just some correct manipulation of probabilities. And what I realized is that they use the symmetry of this definition of the joint probability, or this formulation of the joint probability, to be able to infer something about a variable which is not measured given the measurement of another variable. Specifically, they use this Bayes rule by knowing a prior on some unmeasured variable, knowing a measurement, and knowing also this likelihood, and then being able to make some statements on the probability of this unmeasured variable. Now, so graphically, this manipulation corresponds to just multiplying these two curves, and you get this middle curve, which is the posterior, from which you can derive some informed estimate of what the hidden variable is. Now, I would like to quickly go over an example that most of you know in your sleep, I'm sure, but still I will go over it because it's quite instructive and it will allow me to introduce a number of quantities that I will use over and over again in the talk. So here I assume that all these curves are Gaussian. Both these curves are Gaussian probability distribution, that the prior has some mean mu and some width sigma 0, that the measurement is located at x, and that the likelihood has some width sigma. Well, if from these two quantities I calculate the posterior, I again find a Gaussian. As you know, if I multiply two Gaussians, I will simply find a Gaussian with a mean which is simply the weighted average of the two means of these two Gaussians, and the weighting factor is the precision, the inverse square width of each of the Gaussian. Furthermore, the width of this posterior distribution itself can be expressed in terms of the geometric mean and the arithmetic mean of these two widths. And in fact, it's easy to see that it's smaller than either of the two widths. You can rewrite it like this, or with the sigma on top and the sigma 0 downstairs. And so as you go, this posterior gets narrower and narrower. Now, this doesn't tell you how to estimate the hidden variable. It just tells you how to infer this distribution. And to estimate, you have to have an additional prescription. And typically what people do will be to define some loss function, which is some well-chosen or ad hoc function of both the true state and the estimation of that state. And this estimation is found as whichever value minimizes the mean of this loss function given the posterior. Okay? Now, the Gaussian case is somewhat degenerate because for all three of these cases, meaning the L0 loss function, the L1 or the L2 loss function, you get that the best estimation is just the mean of the Gaussian. And this is why I kind of was somewhat cavalier in calling both these S hats, although this is a large S. Okay? Now, what if I continue this process? Suppose I get a second measurement, another x. Well, then I will now take this posterior as being my prior. I will again multiply it by the likelihood. I will find an even narrower posterior, and so on. And so if I repeat this many times, I will find these simple kind of online equations, if you want. And here, in order to write them in a simple form, I've specified the prior as having 0 mean and as having the same width as the likelihood. Okay, but that's just to be able to write these in as simple a form as I could. And so what you see here is that the estimated variable is simply the empirical mean or close to the empirical mean of all your observations. And the width scales like the width of the likelihood, but decreases hyperbolically with the number of trials with time. Okay? So basically the image is that you have a posterior that becomes narrower and narrower with the width going down with this denominator increasing linearly in time. And this is kind of again, a pathology of the Gaussian case that no matter what your observations are, your posterior will, the width of the posterior go down, so you're very, very sure of your estimation no matter what are the specific value of the observations. So all this, I'm sure most of you are perfectly familiar with. The main point for me in mentioning this was to introduce this quantity, which I call the learning rate. Since this is true, since this mean taking, if you want, is true for all times, all trials, I can re-express this in terms of only the last measurement and the estimate at the previous time. Okay? And this will simply be a linear sum of the two, and it's weighted by this factor, eta and 1 minus eta. And this eta I will call learning rate. And because of this denominator here, because I'm taking a mean, then this eta will decrease hyperbolically in time. Okay? Now, so both the width, or both the variance rather, and the learning rate decrease hyperbolically, so after some time I will stop learning, basically. Now, finally, another way, which is important, and I'll mention why, another way to think about this learning rate is that now I can reorder this sum and isolate this s hat at time t minus 1 and say that my new estimate is the old estimate plus some correction, which will scale like what people call prediction error, what I will call surprise, which is the difference between your observation point and your previous estimate, by how much you were wrong. And whatever number you multiply this surprise is the learning rate. So in other words, the learning rate, you can think of it as the ratio of the correction that you make in your estimate at time t with the surprise that you had at time t. And the reason that's relevant is because you can now calculate this learning rate directly from data. That is not a definition that bears on any Gaussian approximation or anything. This is a definition that just bears on the behavior. Okay? So this you should not miss, because I will invoke the learning rate again and again. And a lot of some results, some experimental results will be phrased in terms of the learning rate. So if there's anything that is unclear, you should ask me now. So this is a definition. I just define it, the learning rate, like this. I motivated the definition with this Gaussian example, but now I'll just take it as a definition. So what if now my state, my true state, is not invariant in time? What if it moves? Well, you see that if I apply this prescription, if the state changes, the true state changes over time, I will fail miserably if I apply this prescription, because I will be extremely sure of what I have as an estimate. My learning rate will only become smaller. And so I will take very, very long time to kind of move my estimate to a new correct position. And so most of my work will be an attempt at addressing this problem in the context of human behavior, namely, how do people estimate some hidden changing variable? Now, there are two loosely related parts, and my guess is that I will never reach this part. So most likely I will talk only about this today, which is really this problem I just mentioned. As it turns out, this is work in progress, so I'm kind of more excited about this, so I will be happy to discuss it afterwards with whoever, and I would love to have feedback about this, but I doubt I'll get to it today. So the starting point for this work is an experimental task that we ran on humans, and this is what subjects see. So the red dot, so this is the position. We just consider one-dimensional problem. The red dot is the true position, is your hidden state. And subjects will see this red dot only in trial runs, but they don't see it when they actually do the task. Okay? What they see are these white dots that are samples from a distribution around the red dot. Okay? And the green dot is your cursor, is whatever the subject can control. And so what happens in the task is that you have a new dot that appears. When it appears, it's fat so that you can see it. Then it goes to the normal size. And then you can move your cursor to where you think the red dot is. And then you click on your cursor, and then a new dot appears, and it goes normal, and you move your cursor, and you click, and so on. So to summarize with a little bit of a zoom, this is basically the task. You have a new dot that appears. This is your cursor. You will move your cursor wherever you think the red dot is, the hidden state is, and you click on it, and then it starts again. So it was quite amusing. I was describing this task so the story we gave to people is that to the subjects, that there's some guy that is throwing snowballs at you. So the snowballs are these white dots, and there's a lot of fog, there's a lot of mist, so you can't see the guy, and the guy is a little bit drunk, so he will send the snowballs a little bit randomly, but you're supposed to hit the guy. And the guy can jump at discrete times, and you're still supposed to hit the guy. So I was describing this task to a former physicist, collaborator of mine, who now is managing the biggest investment fund in France. And so he looked at me really in disbelief, and he told me, but this is such a difficult experiment. How did you do to have artificial snow in the lab and so on? So this is basically what subjects see, but I haven't told you what are the statistics that govern this task. So the statistics goes like this. So in this plot, this is time. Time goes upward, and horizontally you have space, and the true state remains constant and then switches punctually at given points. So it switches discretely at given points from one trial to the next. Okay? Now, when it switches, it will switch either to the right of where it is or to the left. So if it's here, it will switch either to the right or to the left. So these two triangles kind of are conditional. Their position is conditional upon where your state is. Now, the subject doesn't see the state. The subject only sees these points that are sampled around the state, and they're sampled according to a likelihood, which is again triangular, around the state. And the reason we chose this triangular distribution is to have an appreciable overlap between this blue triangle and the green triangles. So for example, if you think about this point, it's ambiguous whether it's a draw from this distribution and the true state is still here, or whether the true state has jumped to here and it's a draw from a closer point.
You could have done it with the Gaussian, why triangular?
Right, so so this was the first time I did some behavioral experiment, and after I did this, my respect for behavioral scientists just went up in a discrete jump. Because we tried, as you can imagine, many, many different things, and the first thing we tried were just two Gaussians, here and here. The problem is that when you have a Gaussian, let's say for the transition property, most change points are very close. So in a very real sense, they're not really change points. So we wanted something which is a real change point, hence this bimodal distribution. Now, why not take Gaussians? Is because you have to fiddle a lot with parameters to have a good overlap between the likelihood and the Gaussian. So we tried various implementations, and we had a lot of pilot data, and we kind of settled on this. Now, whether this is the perfect choice, certainly not, but it's the one we picked. It's harder to analyze, but life is hard. So yeah. So now this is the spatial statistics. Now what about temporal statistics? So for temporal statistics, I will rotate this to explain it's more simple. So to explain to you what the temporal statistics are, I will define what I call the run length. The run length with symbol tau is a random variable that is reset to 0 every time you have a change point, and that grows at each trial. Okay? So the run length after a change point is 0, then 1, 2, 3, then falls back to 0 when you have a change point, and so on. Okay? So at any time, you have a random variable, which is tau of t, trial t, and that's the run length. So it's since when you've been in the same position, your true state. Okay? Now, we considered two different temporal statistics. One temporal statistic here is in blue and tells you that the probability of switching at any time is the same. So it's a Poisson, you'll have Poisson distribution of change points, and I label it HI because I think of it as history independent, okay, because of its Poisson character. And the history dependent case is this yellow case, which is a sigmoid. So initially, immediately after a change point, and that's what is represented here, the probability immediately after a change point to change again is very, very small, and it grows after about 5 or 6. Okay? So if you look now at the distribution of intervals, what you see is that for the Poisson case, most of the intervals are kind of small, smaller than 5 or 6, whereas in the yellow case, in the non-Poisson case, most of the intervals are around 10, 11. Okay? Now, something that is very key here is that the mean of the two is the same. So on average, the true state will jump every 10 steps, every 10 trials. The difference between these two cases is really fluctuations around this average. Okay? So is the task clear? Okay. That's right. That's right. So the subjects will play the game either in one condition or in the other.
And then you have the same subjects do both of them?
Yes. In different, but trained also on the same. So there's a big training phase, and then there's the actual game, actual task.
So from the training phase, the subjects can understand that there are different statistics.
Okay, so the subjects is essentially told the story I mentioned before about the snowman, but is not told anything about the statistics. Neither about the triangular shapes nor about the temporal statistics. It just knows that it will jump.
But in the trial phases, they see where the...
Okay, so there's a good question. So there's a very short initial trial phase, which is passive. So they see the red dot kind of jump. They see the hidden phase. And this is completely passive so that they understand the task. And this is very short. Then there's a longer trial phase where they learn to play the task. And then there's the actual runs, which are analyzed. Yeah.
You've shown that from one situation to another, it's 400 milliseconds. At the beginning,
Yeah,
does it matter if you give more time?
So I think in this case, we try different things, but I think in this case they're not. There's no cutoff, so there's the fixed delay, but they can wait as long as they want. They just click relatively fast naturally. Yeah. Okay, no. So the switches are random, and they're drawn from either of these two distributions. So in one case, the switches are Poisson distributed. So at any trial, you have a given probability 0.1 to have a switch, and in the other condition, the probability of switching grows with the time you spend since the last change point. Okay.
Clarification: the change probability. This is the true change probability, or this is the estimated?
No. This is all true here. This is all true. This is really the statistics of the task. I will come now to behavior. Yeah.
Are they given feedback?
They are given feedback. So the way they're given feedback. So this is a criticism I get from economists, that they're not incentivized on each trial. Now they're incentivized globally because we pay them. They're also incentivized psychologically, but not every trial. They're incentivized, I think, every 50 trials, something like this, where they get an idea of what their score is. So there is some kind of loose feedback, if you want. Okay, so this is one subject. This is what one subject does. Subject 13 is the red line, and you see this guy is pretty good, and but what you can see immediately is that the learning rate varies a lot. So here, okay, so what are you seeing? So the green is the true state. The blue are the white dots that the guy sees. And the red dots are wherever he clicks his cursor. And the curve just connects these red dots. So what you see here, for example, is that in this event, the learning rate was large, was about 1. Why? Because the guy was here, the cursor was clicked here, the next point appeared here, and the subject decided to move all the way close to the next point. So the learning rate was nearly 1. In this case, however, there was a big surprise, because the guy was here, the observation point was here, but he didn't change, so the learning rate was 0. So the obvious thing to do was to plot this learning rate, the average learning rate, as a function of the run length over for each of the two conditions. And this is the first experimental result. It's funny that from my mouth comes the first experimental result we have, but this is it. So what you see here is that the blue case, which is the Poisson case, essentially the learning rate, as in the example, the Gaussian example I showed before, goes down. So the longer you wait, the more sure you're of your estimate, the less you move on average. Okay? Whereas in the yellow case, the learning rate goes down. In fact, it goes down more steeply than the blue case, and then it moves up. And you can think of this as kind of the anticipation that it will move, or the awareness or some kind of knowledge that it will move. It's similar to when you're at a red light. Well, as time goes on, you're more and more ready to start the car because the green light will come on, and that's kind of a similar thing. Still, it was interesting to us that the subjects would behave differently based on the fluctuations, again, of the change point, not their mean length of the intervals. And furthermore, we didn't say anything to the subjects. So all of this happens implicitly, and when we debrief them, they're not aware of the different conditions. In fact, if you play the game, you don't really feel the difference. Both seem quite random. Okay? Yeah.
Even the blue is not. There is some plateau in the middle.
There is some plateau. I'm not sure how true this plateau is because the data are very, very noisy. So you're right. So this is something to explore, whether it could be noise from either the subject, but it could also be noise from the stimuli.
Maybe it's not noise. Maybe this is a strategy.
Could also be strategy, but I'm just saying it's not. The error is big enough that you don't know whether it's a strategy or not. I agree with you. There's a question. It's not obvious though that it's a strategy. One thing I should point out is they all do the same series. So the series is frozen and all the subjects doing it. So there is more noise than you would expect if you say change the series. Yeah.
So this is average over many players or many.
This is average over many players. That's right.
And over the duration.
And over the duration. That's right. Exactly. So there are questions attached to it. We can discuss them, but yeah.
There's something which is not clear to me. It could be that the subjects are employing exactly the same strategy, but the statistics of the experiment as a function of the run length are different in these two conditions.
So this is a very good question that I will address, but in 2 slides or 5 slides or something. Yeah. Yes.
This includes most of the trials where they don't include the subject doesn't actually make any correction?
This includes everything. Yeah, this includes everything. So
mostly it's 0, right? The learning rate is mostly
No, it's not mostly 0. Well, you can see what it is. So if the average is 0.3 or 0.25, it cannot be mostly 0. Especially that it's never larger than 1 or very, very rarely. So if you have an average of quantities that are small.
How often does the subject change?
So that's a very good lead to my next point. So that's exactly what I was going to mention here. So the second thing that is very striking in this kind of single trial is that there are these stretches of time where the subject doesn't correct. So the subject just repeats where he is. And in fact, if you draw a histogram of the corrections, what you find is what you say, which is that you have a big weight at 0. You have an inordinately large weight at 0, yet this weight is about 20%, 30%. So we call this the repetition propensity, which is basically this weight at 0 is the probability that you will repeat, if you want. And what we find, ignore the solid lines for now, what you find is that the subjects have a repetition propensity on the order of 10, 20, 25%. And if you squint, you could admit that, again, there's a somewhat different behavior in the two, for the two temporal statistics, although the behavior is less discriminant than before for the learning rate. Okay? So how are we to understand this behavior, and in particular to answer the kind of questions that Yoram had? So the first thing that makes sense to do is to look at the benchmark model, which is the optimal Bayesian model. And as I was mentioning before, you obtain the posterior given all the observations that I summarize here as Xi as a product of the likelihood and the prior. Okay? Now, a little detail here is that in the Poisson case, which is most of the literature on change points, you always have the posterior only on the state, on the hidden state. Once you have non-Poisson statistics, you have to include also inference of the run length, okay? And in the Poisson case, obviously, this decouples. These two are independent, and so this is just a product of two probability distribution. But in the non-Poisson case, you have to infer over this plane and not only over each of the one-dimensional variables. So this is quite simple to write. This likelihood is simply the blue triangles I had drawn for you. And the prior will include the cases where you have and the cases where you don't have a change point. So if you have a change point at just the trial before, your tau is reset to 0. And you have to sum over all the probabilities of having a change point, which involves the probability of having a change point given tau, and all the possible states that you're in. Okay? The other piece of the prior is you did not have a change point, so that comes with probability 1 minus q. And all you have to do is to slide from tau minus 1 to tau. So your tau, you just get older by one trial. Okay? So the intuition is here. So here, what you see here are 4 panels for different taus. This is tau equals 0, tau equals 6, 9, and 10. And on each panel, you have a dashed line, which is the probability over S at the preceding trial. Okay? And then you see this measurement, this red tick, and the blue and yellow lines are the probability distribution after having seen this tick. Okay? And what you can see here is that as tau becomes bigger, of course, this distribution becomes narrower. But the other thing that you see is that for small tau, like here, this point, this observation will create some probability weight here far from your former estimate in the blue case, in the Poisson case, but not in the non-Poisson case. Whereas at long times, the probability weight that it creates far, this Bayesian equation is bigger for the non-Poisson case. Okay, and this agrees with the kind of picture we saw with the learning rate. So this is just to illustrate basically the mechanism, if you want, of this Bayesian update. Okay. So what does the comparison with the human behavior give? So this is what you see. Oops, sorry. What you see is that here the human behavior is these dashed lines, and the optimal Bayesian model are these solid lines. Okay. And what you see is that qualitatively there is an agreement. The blue line goes down, the yellow line goes down more, then crosses the blue line, goes up. Similarly, there's a qualitative, at least, agreement for the repetition propensity. Both things go up, then the yellow line goes down. Now, obviously, quantitatively, the model is very, very wrong. And so for the rest of the talk, I will discuss how one can understand this and explore various models. But not optimal.
How come that you have the propensity to repeat at all in the
So this was okay. So it's not continuous because you have pixels on the screen. Now the question is, how come it's right? So I was also surprised that they stay within a pixel. Even kind of motor noise or something doesn't bring them out of the pixel. And
I'm
but
talking about humans. I'm talking about the model.
no, that's because of the pixels. Models because of the pixels. However, but your question kind of leads to another interesting question, which maybe now I'll mention quickly, which is there are various ways you can design the task. One way is you take your cursor and you leave it where it is, and then the guy has to move it and click. The other way is you reinitialize always the location of your cursor. Now, both things have their problems. If you leave it there, maybe you increase the chance of repetition. If you move it away, you maybe give a bias or you change the fluctuations. What we did is to leave it there. Now, this repetition propensity is a very, very kind of widely observed phenomenon. In economics, one can think of it as what economics calls stickiness, and there are many, many examples of behavioral tasks where a phenomenon like this shows up. So I think even if it weren't one pixel and we disturb things a little bit, you would see slightly broader peak, but the peak would still be there.
But again, you're talking about the behavior or talking about the model?
The behavior.
But the model...
It's pixelated.
Just because of
Yeah. Okay. So the rest of the talk will be just exploring various suboptimal models for this. And when I was thinking about these suboptimal models, it really reminded me of this first sentence, this incipit of Anna Karenina, which you all know, I think, is all happy families resemble one another. Every unhappy family is unhappy in its own way. So all optimal models resemble one another. Every suboptimal model is kind of unhappy in its own way. And so what I'll do is I'll kind of explore a succession of suboptimal models. So the first thing, which is maybe the most obvious, and will address your question, Yoram, is this is a complicated task. As you pointed out, these are not Gaussian, they're triangles and so on. Well, most probably the subjects get it wrong. They don't have exactly these triangular shapes in mind and so on. And so the first thing we did was to systematically vary all parameters. So I will spare you this supremely boring exercise. What I'll mention is that what has the most effect on the behavior is varying the character of the temporal statistics. So what we tried, for example, is to change the offset, so change the mean, have a mean which is not 10 but 6 or 20, for example. We did things more systematically than this, but I'll just show you some examples. We also changed the slope to see how sharp the change in the probability becomes. And what you can do is to derive a number of curves, and none of them really model human behavior well. Still, this was a useful exercise because of your question, which is here what you see is 3 pairs of curves. Each pair, the 2 colors, refer to the model with which you're inferring, so to the belief that you have. And, this is one belief, this is one belief, this is another belief. The 2 colors refer to the points that you see, the stimuli. Okay? So what you see is when you go from a Poisson to a non-Poisson stimulus, you change this a little bit. But the change is tiny compared to the change that you get when you change your belief. So this is one way of controlling for the kind of things you're asking. In fact, there are other controls that I don't want to get into now, but we made sure that what we're seeing were not just the stimuli, but really some beliefs. Okay?
Question?
Yeah.
So you compare the learning rate and the repetition rate. Do you also compare error?
Yes, I'll come to that. This will be a big part of the talk, to which I'll come. Okay, so what other things could go wrong, so to say? What other things could be suboptimal? Well, another obvious thing is when you do this Bayesian kind of inference on this complicated task, you have to follow all possible trajectories. In other words, for example, in your mind, you're keeping track of all possible run lengths. So maybe you had a change point right now, maybe 1 trial ago, maybe 2 trials ago, maybe 3 trials ago. And when you move from trial t-1 to trial t, you have to update all these probabilities, okay? So that's obviously computationally costly. And so what one can think is that maybe people have limited memory, employ limited memory, don't go through the trouble of storing all these possibilities. And there are, in fact, two examples of such models in the literature that I mentioned in passing. One is to say that people only keep track of a mean runtime. So basically, they collapse their distribution as a distribution only about the state, and they're sure that the run length is the mean run length. Another possibility is to say, well, people have a set of reference run lengths. So maybe you think 1, 3, and 6. These are the possibilities, and you will attach to each of these possibilities some distribution over S. So pictorially, this is what happens. You think that the full probability weight is on the mean, and you change the mean, or you divide your probability weight on reference run lengths, and you change the probability weights. So neither of these work well, and also I found them quite artificial. So we came up with a hybrid, if you want, between the two, or kind of something that is includes both aspects. And what we suggest is to say, well, just keep track of the most probable run time. Okay, so you have two run lengths. Let's say you decide I keep track only of 2, and both of them can move, and the weight on both of them can change. Okay.
Many other options.
They certainly are. Yeah.
Probably some sort of an approximate estimate of the runtime based on some past history.
Right. So. Right. So this is this character. That one. Right. So you could do a running. You could, instead of doing a mean, you could do some. What do you mean, the estimate, which would be different from this?
Well, I don't know. I can have an approximate distribution, approximate sufficient statistic in some sense of the past interval. Give me a prediction.
So sure, there are many ways to. Basically, you're updating a whole function, and there are many ways that you could say, well, I update a reduced quantity that represents this whole function. And I will suggest a few of these ways, and certainly the list of things I will suggest is not exhaustive. Because of various reasons, they seem natural to us, and I will try to give more arguments of why, but certainly there are other possibilities.
But you assume that the subject estimates, it doesn't keep track of distribution, just estimates at any given time.
So I will show you exactly what I mean here. So what I mean is this for this model. So in general, I can always write this posterior as a sum of posteriors on S, which are attached to some given tau, right? So what I say that in this model, if I marginalize over S, I get some probability weight for each tau, and I will just keep the n highest ones. And n is a parameter in my model.
So if n is infinite, then
You get back to the optimal model.
the optimal.
That's right. Exactly. So basically, this is what you do. You kind of truncate these, and you just keep this one and that one, and you get this image.
Is this precisely what people sometimes call the particle filtering, or
I will come to particle filtering. You could think of this as particle filtering in time, and the last model I will show will be particle filtering in time and space. Yeah.
But when you truncate,
Yes.
you keep the d's as the true one, or you update them?
No, you just renormalize them. That's all.
That's all.
Yeah, that's all.
No.
No.
Is it the best?
What do you mean? Is it the best?
Is the optimal truncated estimate?
I don't know optimal given what prescription,
Limited memory.
right?
What would be the optimal case?
But you have to tell me what you mean by optimal.
Minimizing the error.
So I haven't done this calculation. Well, you mean you fix a parameter n, and you so you can fix the parameter n and then minimize the error and see how you would truncate. First of all, I didn't do this calculation for the reason that my point was not to I think it will become clear when I introduce noise. But my point was not to try to have some optimal prescription or some principal prescription, but really to fit human behavior. having said this, I expect that if you did that exercise, you would probably find that this is close to optimal. Yeah.
However, this is very similar to other experiments we've done here. For example, oddball tones.
Very much so.
Or,
Yeah.
tapping.
Sure.
Things like this, where we know that essentially we believe that the brain is actually estimating some sort of a crude approximation to the model. And working with this knowledge.
Sure. So first of all, I completely agree with you. And in fact, the second part of my talk, which I probably now certainly won't get to it, is actually exactly based on this oddball kind of stimuli. So it's a discrete setup and so on. So I would love to discuss that second part with you. Now, this is one possible crude representation of this probability distribution. Now, you may have other kind of prescriptions in mind, but this is one possibility for a crude description. So when you do this, these are the kind of things you see. So you see that the repetition propensity increases, obviously, because you're making it cruder, as you say, so you will tend to repeat more. You're kind of reducing the space of possibilities. However, the learning rate goes down, and that's also understandable. And if you remember, the learning rate of the optimal model was already too low, and so this will not quantitatively fit human behavior well. Okay. Now, there's a much worse problem conceptually than this, is that all these models I discussed until now are deterministic. If I give you a series of stimuli, at every time you will come up with a given estimate. And if you look at subject's behavior, the subject behavior is variable. So what you see here is 1, 2, 3, 4, 5 successive trials. The true state is here and doesn't move in these 5 trials. The observations, the stimuli are these blue ticks, and the subjects respond these red ticks. So what you see is that there's quite a bit of variability, and none of these models will give you any variable behavior. Okay? So now how would you, in that framework, in that way of thinking about inference, how would you come up with variable answers? Well, the most common assumption is to say that there is noise at the output. And so even if you infer some posterior distribution, you will not be able to maximize precisely, but you will instead do some other random procedure, which is, for example, sampling from this distribution, which would give you trial-to-trial variability. Okay? Now, this is the most common proposal, but it's not the only one. In fact, you could have noise much earlier on in the process, and you could imagine that the inference process itself is noisy, and so at each trial you generate some noisy posterior. Okay? So in order to kind of disentangle this, it's important to look a little bit more closely what is the character of this variability. And what you can see here already is that as you wait, this variability becomes smaller with time. And you can see this here also if you plot the standard deviation as a function of the run length. Again, you see that the standard deviation in the Poisson case goes down, whereas again, as for the learning rate, the standard deviation of the subject goes up in the non-Poisson case. Okay? So this is kind of very suggestive that there is some underlying mechanism that is similar to the one that governs the learning rate that also governs variability. And in fact, if you compare the subject responses, so these solid lines here are the same as here, if you compare it to the standard deviation of the Bayesian posterior, you see that at least qualitatively it's similar. You see again the standard deviation of the Bayesian posterior goes down in the blue case and goes back up. It has this smile shape in the yellow case. Okay? Now, more striking than this is probably this little movie. So how do I? Okay. So here what you see, these are the stimuli. The blue line is the Bayesian posterior, and the red line is the smoothed out response of the subjects. And what you see is that they're very similar. At least the scales are really comparable, right? So it really looks like the subjects are kind of sampling from the posterior, if you believe this movie. So that's that's the kind of standard proposal that I mentioned before, and that's the first thing we tried. So what we do is you can marginalize over tau, and then you just sample over S to find your estimate. So obviously, by construction, you will get the error that behaves like the standard deviation of this posterior. However, it's quite dramatic what happens, for example, for the repetition propensity. Obviously, if you just sample something, you will not repeat. Okay, so the repetition propensity goes down very, very much. There's no reason in the sampling model whether you would repeat. So, okay. So this is the learning rate, the first quantity introduced. This is the repetition propensity. So the probability. Okay, sorry. So this is the Bayesian. The solid lines are the optimal ones, and these are this one, the sampling one. Yeah, exactly. And in the case of optimal, of course, the optimal is 0 standard deviation. Yeah. Okay. So this, at least to explain the phenomenology that we have, is not satisfactory. You would have to add some bells and whistles. As such, is not enough. So then we reverted to look at the other possibility, which is whether you have maybe some kind of noisy inference rather than a noisy output. Okay? And one thing that seemed natural to us, and that kind of goes back a little bit to Chaim's question about the choice of this truncation, is to say, well, maybe people don't truncate in a deterministic way the history, but they sample over the most likely histories. So most of the time, they will just pick the most likely run length, but once in a while, they sample a run length that is quite improbable, but that they could have represented mentally. So now I will, instead of keeping, so again, I have n as a parameter, so instead of keeping the n most likely run length and reducing my distribution like this, I will sample n run lengths from my distribution. And when you do this, you see that the learning rate grows as compared to the optimal case. The optimal is in purple here. The repetition propensity also grows, and you also have some error, so some fluctuations that depend. And the 3 lines are for different values of this parameter n. Okay? So of course, as n goes to infinity, it will converge to the optimal line, to the optimal case.
And the repetition is that?
No. So you repeat more, so that's what you want. So right. So this is repetition. Sorry. Yeah. This is learning rate, this is repetition, this is standard deviation. Yeah. So the optimal, the purple here is optimal. Okay? And then blue is Poisson, and this is non-Poisson. And these 3 are for 3 different parameters, the dotted, dashed, and solid. Okay? Now, here, basically what we do here is we say we have a set of, the true distribution has all the possible run length with non-zero probabilities. From it, I will sample a few, maybe 1 or 2, and I will store this, if you want, in my internal computation. Now, even when I do this, I'm still representing a whole distribution over S, right? So to each one of these run lengths, I have a whole distribution over S. So it was kind of a joke to say that it's so much better because, yes, I'm truncating in time, but in space I still keep a whole distribution, so it's still quite costly computationally. So we wondered whether we can make it this truncation even more radical and also truncate things in space. And I think Joachim asked about particle filters, and that's precisely what these sequential Monte Carlo sampling or particle filters approaches do. So why is it called particle filter? Because you will think of your posterior, or rather you will force your posterior to be a sum of delta functions. So you have delta functions over tau, delta functions over S, and some weight, okay? And the parameter in this model is the number of particles, and a particle is given by this triplet, which is its position, its lifetime, and its weight, Okay? Now, if you take such a posterior, and I put the tilde on to indicate that this is this approximate form, and you update it in the correct Bayesian way, you can rewrite it in a very nice way, which is the sum of some number that does not depend on the variable, so it doesn't depend on s and tau, times a function that depends on s and tau. Okay? And if you look at this function is simply the Bayesian update of one particle located at this position. Okay? So this has a simple interpretation, and what happens is this particle either stays there or you think it jumps. Now, if you think it jumps, there's a continuous transition probability. So this thing has a delta peak and a smeared part, which is continuous. Okay? So then it's easy to interpret this number as a new weight. And in order to force back your probability distribution in this form of a sum of delta function, you can just sample a new particle from this distribution. Okay? So pictorially, this is what happens. So here you have successive trials. The vertical line is the true state. So it stays, forget about the true state. The true state is not depicted here. Here what you're depicted is the signals. So these are these blue diamonds. So that's what the subject sees, or the model rather sees. In purple, these purple curves are the optimal Bayesian posteriors. And there are two different models are depicted that are kind of two extremes. One model has only one particle. So you have one delta function here. It stays, boom, it jumps. Okay? And the other model has 150 particles, which has these green lines that unfortunately you don't see very well, but they give you some kind of approximation to this Bayesian posterior. And they kind of flow to this one. Okay? So if you do this, again, you find somewhat similar quantities as you had before. So instead of spending a lot of time on this, let me just kind of summarize all that we have. So we have a fairly large zoology of models. So the inference step, we have 5 deterministic possible models. We have an optimal inference. We have optimal inference but with erroneous beliefs, and we have the various models with limited memory. We then have 2 possible stochastic models that we have examined, which is this limited memory through sampling, and this last model, this particle filter. And for the response selection step, we have the optimal case, which is maximizing or close to maximizing. And we have this other proposal, which was sampling. In addition, we look at 2 additional models that are also stochastic, which are noisy maximizing and noisy sampling. So you either maximize or sample, but then you add a little bit of noise, just some little additive noise that you add to it, okay, and that you can fit. So you can look at this in all kinds of ways, and in a pretty robust way. So, you have 28 models in totals, which is 7 times 4. And if you, in various ways of looking at them, what you find is that the best models are never the sampling models. But typically there are either have the stochasticity in the inference step. So either particle filters or this tau sample. And they come with noisy maximizing. Now, I should say that even though formally that is true, this noise is tiny. It's very, very small. So half of the time there's no noise. Half of the time the noise has no effect. So it's a very, very small noise, quantitatively.
And the models are compared in what way?
Okay, good question. So in this case, we looked at the kind of fraction of variance explained or unexplained, if you want, on these 3 quantities. So but then we did a control, which is choosing pairs of these 3 quantities. So that's just to make sure that this is at least reasonable to look at all 3 at the same time. Now we're looking at doing more Bayesian kind of model selection approaches, but it's quite difficult with these kinds of tasks and models.
You optimize per subject, you average over all subjects.
In this case, unfortunately, we don't have enough data to do it per subject. So in this case, we do kind of an aggregate. I suspect from what I've seen that if you did individual subjects, you would find similar things. At the time, I wasn't aware of how noisy people are, and so we simply don't have enough data.
We don't take into account heterogeneity.
No, not in this analysis. Yeah. But that's certainly some very relevant thing to do. Okay, so before concluding, let me just make a couple comments. These are not the only models, as Tali has pointed out a number of times, but there are other models that are possible and that are actually much more trivial than the kind of models Tali was referring to. One is that you could imagine you have a repetition propensity which is completely stimulus independent. There's just some probability to repeat your answer, and you see this in some animal tasks, for example. Another model that we looked at is that you could assume that you have some motor cost that depends on by how much you want to change your answer. And if you don't have to change your answer much, it may just not be worth changing at all. Now, as a story, it's a nice story. Mathematically, it's not very compelling because that's just a kind of way to put in the result in some words. So, but as a story, maybe it's not untrue. And the last comment, maybe I would like to...
You check the possibilities, or you argue that they are not interesting?
I didn't check this one. I checked this one, and it can explain the data fairly well. But I didn't take it very seriously. Because there's no real computational framework. There's no real reason. I mean, it's just a story.
So if you just add motor cost, you think it's not computationally viable?
Well, you could... No. So you need to add motor cost that has some form that depends on...
Which is the displacement.
No. But it has to have some functional form of the displacement, of the correction. And of course, you can choose some form which is not completely ridiculous, that looks kind of nice.
F is not natural.
No, it is quite natural. It has some shape which is quite natural, and you can kind of fiddle it a bit with F and explain the data. You can do that. So I'm saying, basically what I'm saying here is that it is very possible that this is also an explanation that could coexist with the other explanation or replace the other explanations. I'm just saying that I don't have enough of a foundation for it to want to discuss it at least now in detail. One quick comment maybe is that it is difficult often to distinguish some generalized sampling, meaning instead of sampling the probability distribution itself, you sample the probability distribution, for example, raised to some power. So you make it either more narrow or more flat. It's difficult to distinguish with maximizing a posterior that has been perturbed in a random way. The two will give very similar results. And we tried also this model, and it doesn't improve anything, in spite of the fact that it has an additional parameter. So I don't think it's a very viable candidate. Okay, so question? It wasn't my own voice. Yeah.
Question, I can wait until the end of the conclusion.
No, go ahead.
So going back, the whole issue of repetition is very unnatural to discuss. It's all about the pixelation of the screen.
Again, as I said, I think...
So in principle, if you had larger pixels or smaller pixels, prediction is that in all these models, you'll have very different behavior. All these computational models, the fraction of repetition will be very different. On the other hand, you could imagine that from time to time, your participant was not looking at the screen, so he just does the same thing. This would be repetition, just stimulus independent, or even that from time to time, some subjects say enough is enough. I'm just going to press the same thing and get it done with. And all these things can be easily checked if you just change the size of the pixels. And again, looking at repetition, this framework is weird to me.
So I think there are two answers to this. One, okay, Okay. First answer is I think if you change the pixelation, you will still have a peak. It will, become a little bit broader, a little bit narrower. It will just change the size of the peak, but basically you will not change this character that you have a fraction of the time that you repeat. So the qualitative kind of behavior, or even the semi-quantitative behavior, I don't think will really depend on the size of the pixel.
Less explanation comes from different sources.
Right. So now about your stories. Definitely, it's possible that subjects don't look at the screen or are tired or something like this. It's very possible that it's an explanation. I'm not satisfied with proposing this as an explanation unless there is a theoretical framework. There is one possible theoretical framework which was developed by some economists, which is very beautiful and assumes that you will make the decision in two stages. So first you will decide, will I move or will I not move? And then if you decide to move, then you estimate where is your new variable. And both things are associated with a cost. And if you follow that framework, you will find similar results. And so basically this formulation recasts your proposal into a formulation that depends on a cost. Okay? But you're forced then to decompose the action into these two sequential actions, which have to first decide to move or not, and then decide where you move.
And that's what you have also in your truncated model. You have delta tau 0, and there is no computation, and then there is other deltas which comes with probability.
No. There's computation on all of these taus, they couple. So when you do your update, all the taus will couple. And then you truncate for whatever you store in your mind. But when you do the update, they all couple. There's not this separation in these models.
I'm trying to understand, and maybe I essentially you're telling us, look, the humans don't perform optimally, according to this baseline.
Right.
And you're trying to explain why.
Right.
First of all, I wasn't convinced that it's really a significant difference because humans don't have the base model. They don't have the same prior. They have to learn this prior. I'm not sure exactly how much time they had to actually infer any model.
Sure, but that was taken care of by the first analysis where we varied things. So if this were the nature of the suboptimality, we would have found parameters of the statistics, of the generative model that would have fitted the human behavior better. And we did not find them. So you're right, that would have been a possibility. We tried to check it, and the outcome was most likely that's not what's happening.
I simply don't see it in your data, but maybe take it offline.
I don't think you can see it directly in the
Any
data.
experiments of this type where people at least asymptotically seem to converge to the optimum model.
Sure.
Unless there is really another cost that is impacting.
I don't argue that in some tasks people are optimal.
No, they're not optimal, but they
or close to optimal.
Unless there's fatigue, there's cost, there's whatever. But I'm not sure I can get out of your story a clear explanation why they're not optimal.
Okay, so maybe afterwards we can discuss, and you can tell me why you think people should converge, and then you can tell me what you think is a clear explanation. Huh? But I'm happy to chat. Okay, so the first outcome of this work, which has nothing to do with any of this discussion on models, is simply an experimental result. That humans making inference on space are sensitive to the temporal statistics of the stimuli they get. And this has a number of connections. Of course, in nature, most temporal statistics are not Poisson, so you expect people to be sensitive of temporal patterns. But there are other tasks that people have done which also suggest a similar picture. For example, if you want to discriminate a low tone masked by noise, you would discriminate it better if it's presented to you periodically than if it's presented to you randomly. So there are a collection of experiments that kind of address this question of whether we will treat things differently depending on their temporal statistics of arrival. Now, the other broad conclusion that one could infer from this work is that possibly the noise doesn't come only from an output noise, but also or mostly comes from an early on truncation, early on noisy inference. Okay, and personally, I have the same reaction as you. I don't like very much these particle filter-like models. I would much rather explain this through some kind of sufficient statistics or something like this. That's my taste. So personally, I don't like them very much. However, and I'm not sure at all that we do things through samples, through particle filters. However, they do have some advantages. For example, it's a very generic representation mechanism. No matter what probability distribution I give you, no matter its character, you can always decide, okay, I take n samples, this will be my representation. So as a mechanism, it's very universal. It gives a very natural explanation for this repetition propensity. Once you have particles, you're just stuck with your particles, and then you will repeat. If you have 10 particles, a tenth of the time you'll repeat. And in fact, here, somewhat surprisingly, we found that to explain human behavior, we just needed 9 particles. That was the best. That was what fitted the best. And so, indeed, you can fit this with a big dimensional reduction. From function, you go to 9 variables. Why did you smile, Eli? What do you mean? 9 is the magic number, not 7. So, and the last point maybe I want to make is that one can think in these truncation models when you sample as noise as a form of exploration. So what you want to do is you have a complicated structure, spatial or temporal structure. Instead of storing it in mind, you truncate it, and so you keep track only of a very small subset of that structure. But if you do this in a radical way, in a deterministic way, you always eliminate possibilities. If you do it in a stochastic way, once in a while you'll try out these possibilities that you have eliminated in the first deterministic case. So in this case, this kind of inference through sampling, one can view it as a form of exploration in a way to recover from truncation. So I will now skip the rest of the talk. Thank you. Just to get to the acknowledgements. So I did not have time to say all this. Okay. So most of this work was done with a student, Arthur Prat-Karaman, who just defended and is going to Columbia. And we had a lot of advice from Bob Wilson and Jonathan Cohen at Princeton, who had done similar experiments. Yes, that's what he looks like more. And the rest of the talk that you didn't see was done in discussions with Misha, who's cooking breakfast here at his place in Rehovot. Thank you very much.